All right, looking good. Let's go ahead and start going over these answers. So let's take a look here. So metals tend to have 1 to 3 valence electrons. Remember, most atoms actually want how many in total? Tell me in the chat. It goes back to that octet rule. Octet. Most of them actually want how many? Most atoms actually want how many outer valence electrons? Think about that term octet. Yes, yes, yes. I see Tara, I see Rose, I see Alexis. Need more participation. Again, participation is how we learn. Yes, Shane. Excellent. Yeah, they actually want 8 valence electrons. Think about that term oct like octagon or octopus, right? So 8 valence or outer electrons. Metals only have 1 to 3 though, so we want to think about to get to a full octet, are they going to try to fill up that current valence or are they trying to lose to drop down to a shell that's already full? And you're definitely correct. They are going to find it much easier just to lose 1 to 3. If they had to fill up their entire octet, they would have to gain 5, 6, or even 7 more electrons to try to get to a full 8, which would definitely be a lot harder, right? So we know it's much easier for them to just lose their electrons. Awesome, glad you can hear. Yeah, definitely just re-log in if you ever have issues with that. All right, make sure you do have your notes open. Again, I do see a lot of hands raised already. Remember that if you do your notes during class, not only do you get your notes credit, but you actually also get your attendance credit, assuming that you do it during class and that you actually pass it. So you need to do it during class and pass it. We always give you enough answers that you should pass it if you're actually participating and following along in class. Otherwise, you can do your notes later, but in that case, you won't actually get attendance credit. You have to do it during class for attendance. All right, let's go ahead and go over some of our announcements for today.
All right, guys, good morning again. So, as always, just as a reminder, please not share any personal information during class. Your participation is vital and expected. And as always, remember these class next sections are recorded for educational purposes. All right, we are on week 4 of 13 on day 16, right smack in the middle of this week. We are on Wednesday, so we're going to be learning about nonmetals today as opposed to learning about metals yesterday. All right. Coincidentally enough, we are also right smack in the middle of our unit. So after we learn about nonmetals, we're going to be moving on to other aspects of the periodic table. And so today we're going to complete our knowledge about how atoms gain or lose electrons. We're going to identify and look at the characteristics of nonmetals, as well as the characteristics of metalloids, because now that we, at that point, will have learned about both metals and nonmetals, we should be able to put those two concepts together and compare and contrast how metalloids can be similar to either or of those groups. And then by the end, we should get an 80% or higher on our quiz, depending on how well we pay attention and participate during class.
All right, at this point, again, make sure you have your notes open and ready to go. We need 100% responses, either by raising your hand or if you're on a phone or a tablet in the chat, send us a chat and let us know that you have your notes open and ready to go. Here are the links. Again, one will work, one won't. So just click on the one that does. And then otherwise you can get to it from your grades tab, your class plan tab, your announcements, or even your content tab. So there's lots of places to get to it, no excuses. Raise your hands. You have 20 more seconds to get that open or to be communicating with us if for some reason you cannot open it. We're going to go ahead and do something that we did very similar to yesterday, so we should feel pretty familiar with this. Go ahead on the whiteboard, grab your pointer and point for me which of these 3 shells for phosphorus is the valence shell. Again, think about what does the term valence mean? Is it that inner, middle, or outer shell? Point to the valence shell. Valence shell. Go ahead and get your answers up. Your pointers up on the board. Thank you, purple. Thank you, pink. Thank you, other pink. I need more people participating on the whiteboard. You can also tell me in the chat box, inner, middle, or out if you're on your phone. Thank you, green. Thank you, yellow. I see you up there. Thank you, other purple. There we go. Awesome, awesome. All right, looks like yes, most of us are pointing to the outermost shell, and that is absolutely correct. So if you're taking a look at the outermost shell, how many electrons do you see on the valence shell? Tell me the number of valence electrons. Excellent, I see Tara. Ah, that gaseous water will get you, Shane. It's hot and it moves fast. Excellent. Waiting. I see Alexis, I see Rosa and Creek in the chat. How many valence or outermost electrons do we see? Hi, Andrew. Hi, Luca. Make sure you open up your notes, scroll up in the chat, and you should find those links. Need more participation. I only had a few of you so far. How many valence or outer electrons do we see? Take a look on the outside here. Tell me in the chat. Make sure you're participating. That's how you learn. Haven't heard yet from Umeza or Mallory. Thank you, Sophia. Thank you, Matt. Haven't heard yet from Keith or Lauren. There we go. There we go. Lots of people. Thank you. All right. Yes, phosphorus has 5 valence electrons. We can see 1, 2, 3, 4, and 5. And therefore, using our current group numbers, all right, which are the ones on the left, what group number is it in? Yeah, you can try reloading or try to get closer to the Wi-Fi. Again, right now we're just talking about the group number. Awesome. So I see some people getting answers in there. So again, we're going to use the modern naming system, the IEPAC system. All right, so what group number is it in if it has 5 valence electrons? Thank you, Shane. There we go. Thank you, Tara. Thank you, Alexis. There we go. Yeah, so it's in group 15, all right, group 15. It used to be called the 5A group, but now it's called the group 15. That still tells us how many valence electrons are in it, so we still keep it consistent with our periodic table. We know that if we look at the last digit of the group, that tells us the number of electrons. So that last digit is 5, and it has 5 valence electrons. Remember that we are going to be learning about the names of these groups in just a few lessons, so tell me in the chat then, what is the name of this group? That's something that we can just get from the chart. So what is the name of this group? Again, we have the group number, the modern group number. Tell me now, what is the name of it? Thank you, Tara. Thank you, Colleen. Again, get used to using these terms because you will need to familiarize yourselves. No, you don't need to know things by heart usually in our class. There's not a lot that you have to memorize, just like definitions and stuff wise, right? We tend to want you to apply everything, right? So you should be able to look at a chart and be able to apply this information. Excellent. We don't do a lot of rote memory. Yeah. All right. So yeah, this is the pnictogen group. All right, so much like the word pterodactyl, the P is silent, so that's how you say that, pnictogen. And pnictogen is actually Greek or Latin or something. Pnictogen actually means to choke, all right, so it's elements that choke. And the reason why is because nitrogen is actually also in the pnictogen group. So phosphorus and nitrogen are both in the pnictogen group. And ancient scientists discovered that nitrogen, if you're in a purely nitrogen environment, can choke you or suffocate you. So our current atmosphere is like 21% oxygen and, 29% oxygen and 71% nitrogen. So we do have a lot of nitrogen in our atmosphere, but because we have some oxygen, we can still breathe. If it was 100% nitrogen, it would choke us, right? So that's where that name comes from, the term pnictogen. So interesting history lesson there. So again, based on our octet rule, we just reviewed this in our brain stretch. How many valence electrons do atoms actually want? Again, oct being the same prefix that we find in octagon or octopus, all of which have what number in common? Sorry, tell me the total. Yeah, tell me the total. Right, Alexis? Yeah, so in total, they want 8 valence electrons. So phosphorus currently has 5. We just counted those up. So is phosphorus happy? Is it stable? Yes or no? If it has 5 but wants 8 in total, is it happy? Is it stable? No, and this is actually what we saw with magnesium yesterday as well, magnesium being a metal, and we saw how magnesium eventually loses its valence electrons to get to a full shell. Today, though, hint, hint, we're taking a look at nonmetals. Phosphorus is an example of a nonmetal, and we're going to take a look at how phosphorus deals with this problem a little bit differently. So let's go ahead and fill in question number 2. Question number 2, you should have 2 check marks that phosphorus has 5 valence electrons. It is in group number 15, which makes it the pnictogen group. Go ahead and answer that and raise your hands. You have 20 more seconds to get that done if you haven't already. Go, go, go. Raise your hands, or if you're on your phone, send me a chat.
Familiar from yesterday, but just as a reminder, remember yesterday we were looking at the blue elements being the metals. Today we're focusing on the yellow section being the nonmetals. And it's not a coincidence that hydrogen being the exception, that the nonmetals are kind of sectioned off all on their little own corner of the periodic table, probably because they all have the same or similar properties associated with them. But at the bottom here, just reminding that an octet means it has a full shell of 8 electrons. But remember, the octet rule does not always apply, and our one exception with the noble gases being helium, which is perfectly happy with having 2 electrons. So the main concept with nonmetals is that they love to gain electrons. They're very, very greedy. So having 5 to 7 valence electrons, they want even more to make 8. So therefore, it's easier for them to gain those electrons to complete their valence shell, to make that really nice octet. So with the example we have down here, oxygen being neutral, right? Its actual preferred state that it likes to be in is actually an ion known as oxide, which is O2 minus, because it's gaining those extra 2 electrons to complete that outer shell. All right. So nonmetals, because of this, have certain properties that are different from metals. So first off, nonmetals are generally non-lustrous, meaning they're not very shiny. They're brittle and they're poor conductors of heat and electricity. So that entire first bullet point, all of that is basically the opposite of what metals were from yesterday's lesson. Next, they come in a wide variety of colors and appearances, some being transparent like this diamond made out of carbon, and colored such as this sulfur or this pile of red phosphorus we have in the center. Notice how the carbon can actually come in 2 variations, being coal and diamond, right? The diamond being very a pretty gemstone, and the coal being a very crusty black rock type structure that we can use for fuel for multiple uses. And then the last bullet point being that they are often liquids or gases at room temperature. This we will be able to see with the next example, but think of sulfur, how every time, I don't know if everyone's visited the La Brea tar pits or held a sample of sulfur in a vial. Sulfur is always fuming, and that's because it's giving off a gas of itself that you're able to smell in the air. So here for iodine, it has 7 valence electrons, which means it always needs 1 more to complete that octet. The vial here is what you'll typically see is it's stored as. We have this little collection of liquid at the bottom with a purple vapor collecting at the top. If we are able to freeze it and condense it down to a solid form, you'll see that it's able to take this form that actually looks very similar to coal. This, again, very brittle, rocky, black type of material. But again, confirming that it has that property of nonmetals, being that it lacks that luster, right? It is not shiny. Go ahead and use your whiteboard tools, which are on right now. Put a box around the option that is most appropriate for completing this statement. So nonmetals that tend to have 5 to 7 valence electrons, so they prefer to what? Do they prefer to gain or lose, or keep the same number? The correct answer here, the most accurate one, is that they're going to love to gain their electrons to fill that valence shell. So for number 3, go ahead and mark that in your notes. I will set a timer for us, and be sure to raise your hand when you're done so that we know we can move on.
Excellent. Let's go ahead and actually begin to apply this here. So we did this yesterday with metals. We should be pretty confident in how to do this with non-metals today. So we're going to do a practice problem together, and then you need to do the next one on your own. So make sure you really understand this. Which of the following atoms is most likely a non-metal? Remember, non-metals already have most of their valence electrons. That means 5 to 7 outermost electrons. So find the atom down here that has 5 to 7 outermost electrons. Circle, point, or identify it somehow using your whiteboard tools up on the board. Yes, I would totally agree here. The answer here should be this first one, and we can see how many valence electrons does it actually have. Let's analyze it together. Again, ignore everything in the center. We're just looking at the outermost shell. Tell me in the chat, how many valence electrons do you actually see? All right, so just in case we were jumping on the bandwagon and we're not 100% sure, we're going to make sure to break it down for everybody so everybody can feel confident. Yes, Shane, Tara, Colleen, Alexis, thank you. Let's get more participation in the chat. Thank you, Mesa, Jordan, Creek, excellent. Bryant, yes. Yeah, it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. So it already has most of its valence electrons. It just wants to gain a few more. Tell me, how many more do you think it'll want it to gain? All right, let's practice that as well while we're here. How many more do you think it will probably want to gain? Yeah, to get to a total of 8, that means it needs 2 more, right? So it has 6. We just need to add 2, and that would get us to our octet, and that would make it happy and stable. So somehow it's going to steal those electrons from somebody else during the bonding process to try to get to a total of 8 valence electrons. Therefore, it's definitely a nonmetal. These ones over here are actually metals. All right, so you can see here, let me type that up there. Metals. So you can see here that this one has 2 valence electrons and this one has 3, 1, 2, 3. So since they only have a few valence electrons, I like to think of it like the electron poor get poorer and the electron rich get richer. So since they're electron poor, they only have a few of their valence electrons, they're actually going to give them away. So these ones will actually give them away to a different atom during the bonding process and try to get rid of them, because just by getting rid of those few electrons, they'll drop down to a shell that's already full, making them happy and stable. Go ahead and give me a smiley, medium, or sad face if that breakdown makes sense. Again, I know we had a lot of the correct answers, but I want to double check that we're not just jumping on the bandwagon, but we're really understanding the concepts behind our answers. All right, looks like most of us are pretty confident. If you're not yet confident, again, we're just looking at the outermost shell. The outermost shell tells us if it's a nonmetal or a metal. The more electrons it has, the more likely it is to be a nonmetal, because nonmetals have most of their valence electrons. They just need a few more. That is the definition of a nonmetal. All right, this is the answer to number 4. Please raise your hands for number 4. I see a lot of you already have, but just in case, I'll give you 20 more seconds. For those of you that have not yet, raise your hands. Or if you're on your phone, send us a chat. Question number 5. This one is a complete on your own, so please don't put answers in the main chat. But just to help you out again, this is very similar to our previous problem. Which of these following atoms is most likely a nonmetal? Again, nonmetals want to gain more electrons because they already have most of their valence electrons. So we're looking for the atom that already has 5 to 7 outermost electrons. So that's a hint based on what we just worked on to help you out. So go ahead and work on question number 5. If you want to check your answer, we're in the Q&A area. Please don't put answers in the main chat though. You have 30 seconds to raise your hands for this one. Metalloids are kind of a weird one, right? So we've talked about metals and nonmetals so far. I think we're feeling pretty confident about that. Metalloids are where things get a little bit weird because metalloids act like both depending on the situation. So they have properties of both metals and nonmetals. The reason being because they have a medium amount of valence electrons. So sometimes they can gain electrons, sometimes they can lose electrons, sometimes they can share electrons. Sometimes the same element, the same metalloid, will do different things depending on its situation. It could gain or lose electrons. So metalloids are not only kind of in between nonmetals and metals in terms of properties, but on the periodic table, they are also literally in between the metals and the nonmetals, which kind of helps us remember how they are in between. All right, so let's go ahead and take a look here. All right, I'm going to share this with you up on the whiteboard. We're going to share our ptable.com. Again, I highly recommend that for this course you bookmark ptable.com because we use this a lot. And as we're doing our next project, you will be using this a ton. So make sure you open up ptable.com. Or sorry, save ptable.com. All right, so taking a look here, this is our periodic table, and if I hover over where it says metals at the top, this periodic table is amazing because it highlights all of the metals for us. So we can see over on the left, you can see all of our metals in orange, yellow, reds, and blues. In fact, most of our periodic table is made up of metals, all on the left-hand side. Now, our nonmetals, which we're learning about today, we just learned about, are on the right-hand side. There's not as many nonmetals. They are the ones that are green and purple right now. So they are the opposite of our metals. And again, our metalloids are literally right in between. So if you ever have a hard time remembering that metalloids are kind of like metals and nonmetals, just look at our periodic table and you will see that they are literally halfway in between. So this is called the staircase or the zigzag, all right, the staircase or the zigzag. And so you can see those different metalloids right there, and we're going to talk about those properties. Yeah, that symbol right there that Mr. Ramirez has is the cougar, which we are the Insight Cougars. I don't know if you knew that that was our mascot. All right. So go ahead, give me a smiley or an emoji in the chat box if that makes sense, talking a little bit about where we find metalloids and how they're related to metals and nonmetals. And then we're going to go ahead and talk about their properties as well. Talking about their properties now, you can see an example of boron up here. Boron is an example of a metalloid. Just so you know, the actual definition of metalloids is a little bit contested within the scientific community. So there are 6 metalloids that are 99% of the time included in the metalloid group by all scientists. But every once in a while, there are some other ones that we also throw into the metalloid group, depending on how we define metalloids. So they're, again, kind of weird. They're kind of a weird group, and so they're hard to define, as well as they're hard to always figure out their exact properties. So just so you know that, but there are 6 of them that we tend to consider metalloids, including boron. So you can see here that boron is definitely shiny, which is a lot like a metal. Remind me again, what's that word that means shiny? Starts with an L. Tell me in the chat. Let's practice that vocab. Not quite, Tara. You're missing a couple letters there. There we go. Lust is a little bit different than luster. Yes, they are lustrous, right? They have luster. Lustrous, all right, which is much like a metal. However, they are brittle, which is more like a non-metal. Remember, metals are supposed to be ductile and malleable, meaning that we can stretch them into wires, we can pound them into sheets, that we can change their shape without them breaking. Boron, though, if you try to change its shape, it's just going to crumble apart. It is brittle. Brittle means it'll crumble apart. Now, they are all solid at room temperature, which is more like metals. Okay, so this is a little bit more like metals because almost all of our metals are solids except for mercury. And our non-metals tend to be liquids and gases. There are some nonmetals that are solid, like sulfur or phosphorus or carbon. We saw those earlier. But most nonmetals are actually liquids or gases. So they're a little bit different. So this is a little bit closer to a metal property. Yeah, they're kind of their little subspecies, exactly. That's a great way to think about it. Now, in terms of conductivity, ability to carry energy, we learned about 2 types. We learned about heat or thermal energy, as well as electrical energy or electricity. And they're in between in terms of heat conductivity. So they're not amazing like metal conductors. They're not terrible like non-metal conductors. In terms of electricity, if they are able to conduct electricity, which not all of them can, which would be more like a non-metal. But if they can conduct electricity more like a metal, they usually can only do it at higher temperatures, or they're just not as good at as metals are. Go ahead, give me a smiley, medium, or sad face based on how you feel about that. Again, metalloids are just in the middle. They're in the middle in terms of valence electrons. They're in the middle in terms of properties. Okay, yeah, so you understand what they are. They're still a little bit confusing. That's totally fine. I hear you. So we're going to take a look at a couple examples and let's see if that makes us feel a little bit more confident. All right, let's go ahead and go over those. Oh, sorry, let's answer number 6 first. So number 6 is that metalloids are solid at room temperature, right? That's one of their properties, at least the 6 that we consider metalloids all the time. Go ahead and raise your hands for number 6, and then we'll go over an example. You have 20 seconds. Go, go, go.
Other than the ones that scientists continue to dispute over, there are 6 commonly recognized elements that are considered metalloids. One being boron with 3 valence electrons, silicon and germanium having 4, arsenic and antimony having 5, while tellurium having 6. So you can see that based just on the sheer variety of metalloids that can have different numbers of valence electrons, right? They could either tend to want to lose or gain. Or when it comes to silicon or germanium, right, having 4, which is half of 8, right, it can actually do both, which is why silicon just so happens to be one of the key elements that we need to use, or that is critical for making computer technology. So first of all, silicon is shiny and lustrous like a metal, as we can see in this picture. It's a very beautiful sample of element, but it is not ductile or malleable. So we can't bend it or shape it into wires or bowls or pots or something like that. But it is very useful to making materials that can be used as what are called semiconductors, which a semiconductor, all that means is that it conducts electricity at a rate between a conductor and an insulator. So it's very easy to control the rate at which electrons travel on a circuit board made of silicon. All right, this is what is allowing us to really just communicate right now, because every piece of technology that we're using to do school right at this second, right, it involves at some point some processor or transistor or capacitor that is utilizing this semiconducting technology. Right. If you want to think about the name Silicon Valley, where all the tech companies are located, that is exactly why it is named that.
All right, you know the drill. Grab your whiteboard tools. We have the three terms: metals, nonmetals, and metalloids. Let's go ahead and define those groups overall. And then we also have three examples of each of those. So we talked about silicon, mercury, and iodine. Figure out what are those each examples of and get your answers up on the whiteboard. Here we go. Which one is the only liquid metal at room temperature? Which ones are lustrous and good conductors that lose electrons? Which ones have properties of both, metals and nonmetals? Which ones are non-lustrous, poor conductors that gain electrons? Which example is used as a semiconductor in computers? And which example is a purple gas at room temp? Go ahead and get your answers up there. Go, go, go. Perfect. All right, let's go ahead and pause those stools and go over these answers. It will be cleaned up on the next slide, but let's talk about it a little bit first so we don't get distracted. So metals, again, are lustrous. Lustrous meaning they're shiny. And they are good conductors of heat and electricity. We talked about how they have free flowing electrons. And so anytime you have flowing electrons, that literally is what electricity is. Plus moving particles, we know from our first unit that when we have moving particles, that carries heat. And they prefer to lose electrons because they only have a few. They are electron poor. The electron poor get poorer. They only have 1 to 3 valence electrons. It's easier for them to just lose the 1 to 3 valence electrons. Nonmetals are the opposite. Thank you for correcting that. All right, we had a couple of mistakes, but we did correct nonmetals. Nonmetals are non-lustrous. They're not shiny. They are poor conductors of both heat and electricity, and they prefer to gain electrons because they already have most of them, right? They've got 5 to 7 valence electrons. They just need a few more. They're electron rich. The rich get richer. Metalloids are halfway in between. We learned about silicon being an example of a metalloid that's used as a semiconductor in computers. Semi meaning that it's halfway in between a metal and a nonmetal. Mercury is our only liquid metal at room temperature, and that leaves behind iodine. Iodine is our example of a nonmetal. That is a purple gas at room temperature that has 7 valence electrons, just needs to gain 1 more, which we define nonmetals as gaining electrons. This is number 7. Please raise your hand for number 7. You have 40 seconds to get that done, and then we're going to go ahead and wrap up.
Completely how atoms gain and lose electrons and why they do so. We identified the characteristics of metals, nonmetals and metalloids, and we did pretty well on our quiz, I am feeling, but tell us how you feel. Go ahead, take out your colored pointer, point to where you're feeling about today's lesson. Hopefully it's toward the right end of the spectrum here. Yeah, a lot of awesomes. Very good, guys. I love seeing that. All right, so if you haven't already, go ahead and submit your notes. And if there's anyone that needs to stay behind in case they missed a question, go ahead and do so. If not, feel free to move on to your next class, guys, and we will see everyone tomorrow.